Hello everybody, myself Prasanto Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In the last Power Electronics and Drive class, we have discussed about series inverter, parallel inverter, and also we have discussed single phase full bridge inverter with resistive load and resistive inductive load. Etc. Also, single phase full bridge, single phase half bridge inverter we have discussed in our last discussions. So also we have discussed series inverter and parallel inverter. So today we'll start with the parallel commutated inverter. So basically this figure actually shows a schematic of parallel commutated inverter. So this is the figure, and see, this is choke, these are the 4 thyristors, this is actually load basically in parallel with this is the capacitors, and this is choke 1, this is choke 2. Basically this is the DC supply input, and yeah, this is actually the output where the say load is being connected. Actually what is happening in a classical parallel commutated square wave inverter base that is shown here, so it is being included here for illustrative purpose, since most other circuits utilizes this circuit or a variation thereof, so in addition with the parallel inverter. So the waveform generated and the supplied load is basically a square wave having a peak to peak amplitude of twice the DC supply voltage, and a period that is determined by the say that relates with which SCRs 1, 2, 3, 4 are gets on. So by the relationship is this 4 thyristors 1 through 4 are gated on. The SCRs are turned on in pairs by simultaneously applying signals gate terminals of SCRs 1 and 4, or SCR 2 and SCR 3. So that is 1 and 4 in pair, and 2 and 3 in another pair. 1 and 4 and then 2 and 3. Okay. So actually if SCRs 1 and 4 happen to be the first to switched on, switched on the current will flow from a positive terminal of the source through negative terminal of the source. So this will establish a left to right plus to minus voltage relationship in the on the load, and simultaneously the left terminals of the capacitor C1 will be charged positively with respect to the right negative terminal. So that is actually here, this is shown here. Okay, so so actually capacitor 1 will be charged positively with respect to the right negative terminal, and the steady state load through the various components is determined nearly completely by the impedance of the load. Choke 1 and 2 and SCRs 1 and 4 present very low steady state drops, and therefore nearly all the source voltages appears across the load. Conduction of SCRs 1 and 4 will continue to the end of the half cycle, at which point the gates are removed from SCRs 1 and 4 remain in conduction along with say now so actually continue SCR 1 and 4 conduction of SCR 1 and 4 will continue to the end of the half cycle, at which point the gates are removed from SCR 1 and 4 remain in conduction. SCR 1 and 4 are remaining in conduction along with SCR 2 and 3 that have now been turned on. If it were not for chokes 1 and 2, the action of the turning on the second set of SCRs would place very low impedance, and therefore some momentarily prevent the source from the being short circuited. So that's why this is the choke 1 and 2. So capacitor C1 now discharges with a current which flows into the cathode of HCR1 to HCR2 in a forward direction back to negative terminal of the capacitor, and this direction of the current flow causes HCR1 to become non-conductive, provided that the reverse current through the HCR is of sufficient duration for the HCR to again become blocking. Okay, so C1 simultaneously discharges to HCR3 in a forward direction and through HCR4 in a reverse direction, and this will cause HCR4 to become non-conductive, just the same of HCR1. So this entire sequence is referred to as a commutation, and typically in a modern inverter will occur in a period of time less than 50 microseconds. And during this interval, chokes 1 and 2 must have sufficient transient impedance to prevent a significant increase in current from DC source. So diodes 1, 2, 3, 4 serve two functions. The first is to return any stored energy that may be kicked back from the load to the source, and they also serve to prevent the choke from generating a high transient voltage immediately after commutations. So that's why the diodes are being connected. So this is the diodes. Okay, so so this is actually the parallel commutated inverters. The circuit diagram is described, and the operations also described. So actually one pair 1 and 4 will be conducted at times, and when they will be completed the half cycles, and then this due to this choke still the conduction started of the HCR2 and 3, that is when the gate the supply gate is being turned on. This so still unless and until this say energy is being dissipated, so actually this conduction will go on. So that is actually parallel commutated inverter, and with this actually we will say cover up this parallel inverter and parallel commutated inverters, etc. So next we'll start three-phase inverter. Now we'll discuss about three-phase inverter. So basically a three-phase inverter converts DC voltage into three-phase AC supply. So today we'll learn about three-phase inverter and its working. But before going any further, let us have a look at the voltage waveforms of the three-phase line. So this is in this above circuit. So three-phase line is connected to a resistive load, and the load draws power from the line. So if we draw the voltage waveform for each phase, then we'll have a graph that is shown here. So and we can see the three voltage waveforms are out of phase with each other by 120 degrees. So that is the case. So this is actually three-phase power supply. This is the resistive load. A, B, C are the three phases given to the resistive load. So this is RA, this is RB, and this is RC. So this is actually the waveforms of the three phases. This is the R phase, VA, that is A phase. This is B phase, VB, and this is C phase, BC, and all are 120 degree apart phase difference from A to B, B to C, and that is the case. Okay, so actually now we'll discuss the three-phase inverter circuit, which is used as a DC to three-phase AC converter. So, and remember that even in the modern days, achieving a completely sinusoidal waveform for varying loads is extremely difficult, and it's not practical. So here we'll discuss the working of an ideal three-phase converter circuit, neglecting all the issues related to practical three-phase inverters. So three-phase inverter working. So three-phase inverter circuit and its ideal simplified form will be looked now. So here we are giving a three-phase inverter circuit diagram designed using thyristors and diode actually for voltage spike protection. This is the circuit. So this is a three-phase inverter using thyristors and this diodes. So every thyristors are connected anti-parallel with a diode. So there are 6 thyristors, 1, 2, 3, 4, 5, 6, and these are the outputs. So this is source DC, and this is output ABC, and this is given to this load. So this is actually the three-phase inverter circuit using thyristor and diode. And below we are showing the three-phase inverter circuit diagram design using only switches, and you can see these 6 mechanical switch setups is more useful in understanding the three-phase inverter working than the conversion circuit. So this is actually the thyristor inverter circuit showing switches. This S1, S2, S3, S4, S5 and S6. This is the output. This is input, as I told you here. It is also shown. This is input, and this A, B, C are the three-phase output point where the three-phase load are being connected. So this is shown using the switch. So this is three-phase inverter circuit using switches. So what we will do here is open and simultaneously closes these 6 switches to get the three-phase voltage output for the resistive load. So there are 2 possible ways for triggering the switches to achieve the desired result. One in which switches conduct for 180 degree, and another in which switches only conduct for 180 degree. So let us discuss each pattern below. So first of all, three-phase inverter 180 degree conduction mode. So the ideal circuit is drawn before it can be divided into 3 segments, namely segments 1, segment 2, and segment 3. And we will use this notational in the later section of this lecture. So segment 1 consists of a pair of switches S1 and S2. Segment 2 consists of switching pair S3 and S4, and segment 3 consists of switching pair S5 and S6. So this is actually segment 1, S1. Then later on we are coming to segment 2 and 3. So for segment 1, switches S1 and S2 are in operation. So at any given time, both the switches in the same segment should never be closed, as it leads to the battery short circuits, failing the entire setup. So this scenario should be avoided at all times. So in any segment, simultaneously both the switches cannot be operated. So it cannot be closed because as a result, so this input or battery would be short circuits, failing the entire setup. So let's start with the switching sequence by closing the switch S1 in the first segment of the ideal circuit, and let's name the start as 0 degree, and since the selected time of conduction is 180 degree, switch S1 will be closed for 0 degree to 180 degree. That is shown here. So this is actually for segment 1, and switch 1 is closed from 0 to 180 degree. Okay. But after 180 degree of the first phase, the second phase will have a positive cycle as seen in the 3-phase voltage graph. So that is here. So if you go to this voltage graph, you will see after 180 degree of actually this. So this 180 degree, if it is that, then second phase will be started. So this is actually 180 degree. So what will happen? Let's see. Actually, but after 120 degree of the first phase, the second phase will also have a positive cycle as shown in the 3-phase voltage graph. So switch S3 will be closed after S1, and this S3 will also be kept closed for 180 degrees. So S3 will be closed from 180 degree to another 120 degree to another 180 degree. So it may becomes 300 degree, and it will be open only after 300. So once again I'm telling you, so after 120 degree of the first phase, the second phase will also have a positive cycle as seen in the three-phase voltage graph. So switch S3 will be closed, and after H1, switch 1, so this S3 will also be kept closed for another 180 degree. So S3 will be closed for 120 degree to 300 degree, and it will be open only after 300 degree. So this is actually the case. So see, this is the case. Okay. So for the segment 1, say H1 is closed for 180 degree, but then the phase difference between A and B phase, so 120 degree. So after 120 degree, the positive half of the say second voltage will be there, second phase. So that for second phase of operation is S3 and S4. So S3 will close from 120 degree to another 180 degree, that is up to 300 degrees. Similarly, the third phase also has a positive cycle after 120 degree. So after 120 degree of the second phase, the third phase also has a positive cycle after 120 degree of the second phase, positive cycle. So that is shown in the graph. So if you see, if you go to the first voltage, three-phase voltage diagram here, it will be clear. So this after this is actually 120 degree phase difference. So second phase has been started, and then it will continue up to say another 120 to 180, that is 300 degree, and but after 120 degree of the second phase, third phase will be started. So that is switch S5 will be closed. So that is actually here. So actually see for the third what will happen here. So second phase and then third phase. So the switch S5. So switch S5 will be switch S5 will be closed after 120 degree, and S3 after 120 degree of S3 closing, that is after 240 degree. So once the switch is closed, it will be kept closed for coming 180 degree before being opened. So with that, the S5 will be closed from 240 to 60 degree cycle. So this is actually, this is does 240, then again 60 degree cycle. So that is actually this. Okay. So up until now, we did was assume that the conduction is done once the top layer switches are closed. But for current flow from the circuit must be completed. So remember, the both switches in the same segment should never be closed at the same time. So if one switch is closed, then another must be open. So for satisfying the above both conditions, so we will close S2, S4 and S6 in a predetermined order. Okay. So for completed the current part, so we'll close the other set of the three segments switches, that is for the first segment S2, for the second segment S4, and for the third segment S3. So in such a way, in a predetermined order, so only after S1 gets opened, we will have to close S2. So and similarly, S4 will be closed after S3 gets open at 300 degree, and in the same way, S6 will be closed after S5 completes the conduction cycle. Otherwise, a dead short circuit will be happened with the input, so the battery. So this cycle of switching between switches of the same segment can be seen below figure. Here, H2 follows H1. So H4 follows S3, okay, and S6 follows S5. So this is segment 1, H1. This is S3, and this is actually H5. So H2 follows actually what will happen. So H2 gets it will be closed when S1 will be open, and S4 will be closed when S3 will open after at 300 degree, and in the same way S6 will be closed after S5 completes the conduction cycle. So the cycle of switching between switches of the same segment can be seen below. That is, H2 follows S1, S4 follows S3, and S6 follows S5. So after 180 degrees, so H2 for the first segment will be closed, then H4 for the second segment after 300 degree will be closed, and H6 for third segment will be closed at 60 degree when S5 will be open. So by following this symmetrical switching, so we can achieve the desired three-phase voltage represented in the graph. So if we fill in the beginning switching sequence in the above table, we'll have a complete switching pattern for 180 degree conduction mode as below. So this is like this. H1, H2 for segment 1, then again H1, H2. This is actually for C. S3, S4, then S3, and again this is S5, S6, and okay. So before S6, so it will be definitely S5. Before S3, it will definitely S4, and so on. So actually, so this is the segment of operations of the three segment where for segment 1 switches H1 and H2 are responsible for segment 2, S3 and S4, and for segment 3, S5 and S6. So, but from this actually we understand from 0 to 60 actually H1, H4 and H5 are closed. 0 to 62, H1, H4 and H5 are closed. Okay, and the remaining three switches are opened. Okay, from 60 to 120 degree, from 60 to 120 degree, what is happening? H1, H4, and from 60 to 120 degree, H1, H4, and H6 are closed, and remaining three switches are opened. So this is shown here from 60 to 120 actually. So that is shown. 60 to 120 is H1, H4, and S6 are closed. Others are opened. And again from 120 to 180, H1, S3, and S6 are closed, and the remaining three switches are open: H1, S3, and S6. See, from 120 to see H1, S3, and S6 for 120 to 180. And the sequence of switching goes on like that. Now let us draw the simplified circuit for each step to better understand the current flow and voltage parameters. For step 1, so that is for from 0 to 60. So S1, S4, and S5 are closed. So that is I told you. So S1, S4, and S5 are closed for this 0 to 60. So in this case, while remaining three switches are open, in such a case the simplified circuit can be shown like this. So this is the case: H1, H4, and S5. H1, H4, and S5 are closed. H1, H4, and S5 are closed. So what will happen? So this will be like this. Okay. Okay, all like this. So this is actually so actually VAO. So for 0 to 60, this 0 to 60 VAO equal to VCO equal to Vs by 3, and VBO equal to minus 2 Vs by 3. So VAO equal to VCO equal to Vs by 3, and VBO equal to minus 2 Vs by 3. So we can, by using this, we can derive the line voltages as VAB equal to, what is VAB? VAB equal to VAO minus VBO, that is equal to Vs, and VBC equal to VBO minus VCO, or VBO minus VCO equal to minus Vs, and VCA equal to VCO minus VAO, that is equal to 0. So this is actually the line voltages. You can derive using this way. So actually, now for step 2, for 60 to 120 degree, for step 2 60 to 120 degree, we have seen for 60 to 120 degree, just coming, for 60 to 120 degree, S1, S4, and S6 are closed. 60 to 120 degree, S1, S4, and S6 are closed. S1, this is S4, and this is S6 are closed, while the remaining 3 switches are open. Okay, so in such a case, the simplified circuit will be like this. So actually, this is S1, okay, and S4, that is here. This is the B, and S6 means this. So this is the simplified circuit. So actually, so for 60 to 120 degrees, so VBO equal to VCO, VBO equal to VCO, and VCO equal to minus Vs by 3, and VAO equal to 2 Vs by 3. So by using this, we can derive the line voltages as VAB equal to VAO minus VBO equal to Vs, VBC equal to VBO minus VCO equal to 0, and VCO equal to VCO minus VAO equal to minus Vs. So that is actually step 2. For step 3, actually for 120 degree to 180 degree, step 3, 120 degree to 180 degree. So for step 3, for 180 degree, 120 degree to 180, S1, S3, and S6 are closed, while the remaining 3 switches are open. In such a case, the simplified circuit can be done as below. So S1, S3, and S6 are closed. So this is actually like this. Okay, this is one, and this is another one. Okay, this is another one in this way. So this is the simplified diagram. So VAO equal to VBO equal to Vs by 3, and VCO equal to minus 2 Vs by 3. So for this actually, for 120 degree to 180 degree, what will happen? This will be like this. So VAO equal to VBO equal to Vs by 3, and VCO equal to minus 2 Vs by 3. So by using this, we can derive the line voltages as VAB equal to VAO minus VBO equal to 0, and VBC equal to VBO minus VCO, that is equal to VS, and VCA equal to VCO minus VAO, that is equal to minus VS. So similarly, we can derive the phase voltages and the line voltages for the next steps in the sequence, and it can be shown as in the given figure. So that is like this. So this is segment 1, this is for segment 2, and this is for segment 3. And this is actually the operational residues. So this will be like the voltage waveform. So this is VAO, this is VBO. Okay, this is VBO. As I told you, VS by 3 minus VS by 3 and 2 VS by 3. Okay, so this will be like the form, and this is VCO. Actually, this is VCO. Okay, so VAB, this is VS minus V. So this is VAB. Clear? Okay, this is actually VAB, like this, and this is VBC from VS2 minus VS. So this is like this. Okay, this is like this, and VCA will be like this. Clear? So so this is actually the 180 degree conduction mode for 3-phase inverters. With this, we'll complete this today's discussion. That is, we have discussed so far the parallel commutative inverters and 3-phase inverters, and its how it operates. So it's 2 mode of operation, 180 degree and 120 degree. Today we have covered up to 180 degree mode of conduction. So in the next class we will discuss about 120 degree mode of conduction. Okay, thank you.